Example 16, we already did it. We're going to do it again. It should be easier the second time around, right? This is the last method that we're going to talk about for algebraically evaluating limits. So we've learned all kinds of methods, right? What are they? Just kind of always, never not first. What's first? Direct substitution, yeah. And if that gives you an indeterminate form, meaning you can't determine it, then we have, we have methods for getting around the 0 over 0, such as, what's that? Ratcon, sledgehammer, Jumpman, recognizing Jumpman, good. LCM over LCM, the one we just did in the warm-up, factoring and dividing out, right? And then we have all that trig manipulation using the two that we memorized. Of course, we also can use a piecewise function. We know how to analyze that, and we also know if there's a vertical asymptote. But sometimes none of those methods work, and you're still expected to evaluate the limit without a calculator, and you don't want to just be in doubt and put D&E, right? So then it just calls for, when in doubt, just be clever. When in doubt, be clever. That's what Newton and Leibniz did. They ran into a wall. They couldn't describe how things changed at a given moment, and so they invented calculus. That was exceedingly clever. You don't always have to be that clever. So let's try out example A again. We'll just pretend like we've never seen it. What do we get when we plug in a 0? 0 over 0. Yay, 0 over 0. So again, what's causing the 0 in the top? It's not the 5, right? It's just the x. And there's two of them. So we have an x squared, and then it's the whole 1 minus cosine together in the bottom that's causing a 0. Now, because we're approaching 0 and you see your trig function in there, you might be thinking, I'm going to use either the sine one that I memorized or maybe even the cosine one that I memorized. But if you split it up as x all over 1 minus cosine x, and then you multiply by the 5x that remains, that's just the associative property of multiplication. And what I did is I isolated my 0 over 0 problem together in a form that resembles what I memorized, and I put the other factor, 5x, off to the side, because remember, that's really the same as 5x over 1. So if you multiply it straight across, top to bottom, you'll see you get the same thing. But I'm just going to call it 5x. Now, this one here is not the one we memorized. It's the reciprocal of the one we memorized. The one we memorized had the 1 minus cosine in the top over x in the bottom, and it went to 0, right? So this being the reciprocal, this should go to the reciprocal of 0, which is D&E. And it's D&E because it's some type of infinity. So that's infinity. And direct substitution on the other one gives you 0. And as I mentioned yesterday, this is a great tug of war to watch. If you have floor seats, you're going to get a good show because these are the two titans. Who wins this one? Maybe infinity, maybe 0, but remember, maybe 7, maybe -2. This is another indeterminate form. It's an indeterminate form. It's just another version of 0 over 0. And the reason is, if you bring infinity to the bottom, you keep the 0 in the top, and you get the reciprocal of infinity in the bottom, which is 0. Or if you wanted to leave the infinity in the top, and you bring the 0 to the bottom, you get the reciprocal of 0, which is infinity. So infinity times 0 is just another version of 0 over 0, infinity over infinity. So unfortunately, that doesn't work. And so our little method of splitting it up into what we recognized didn't work. And so we did develop another strategy in this case. And Jake, I think you recommended it. Jake's now on the video. Oh, who said? Oh, okay. Did you say it too, Painter? Oh, okay. So it's teamwork. What are we going to do? What could we do? What did we do in trig when we got something like this? We multiplied by the what you get? Conjugate. Yeah. So now everyone knows what it is, the conjugate. So remember, multiplying by the conjugate not only gave us a difference of squares in the bottom, which I'll show right there. Do I want to distribute the 5x squared into both terms in the top? No, because x squared is still causing the 0, and we can only divide out common factors. So I'm going to leave it factored. But in the bottom, I get a 1 minus cosine squared, which is the difference of squares. But of course, in trigonometry, that also then set up a what? We can use an identity. Yeah, we can use a Pythagorean identity, and 1 minus cosine squared then we can replace with sine squared. So when you have 1 plus or minus a trig function or a trig function plus or minus 1, look to multiply by the conjugate over the conjugate. That'll set up a difference of squares, which should set up a Pythagorean substitution. And now that we have that, we can kind of reevaluate. It's the x squared in the top that's causing the 0, and it's the sine of x, both of them, that are causing the 0. So now we should get excited because now I can isolate the 0 over 0 pieces. Using the associative property multiplication, it becomes x over sine of x. And again, there's no reason to use brackets or parentheses, either one. And then I have another factor of x and sine of x. And then who's left? 5 times 1 plus cosine of x over 1, or just like that. So I like to put the bad guys in the brackets, right, because they're the bad guys. We don't want them breaking out. And the good guys you can put in the wimpy parentheses. Now we can evaluate it, right? What happens to the first factor? By memorization. 1. The second one? 1. And now the last one by direct substitution, 5 times 1 plus cosine of 0. Cosine of 0 is 1, so 1 plus 1 is 2, and then we end up with 10. So what started off as looking like a cosine thing that we memorized ended up really being a sine. So there's like clever technique number 1. It's only clever really if you have to think about it on your own from scratch. Once you see that it's an option, it just becomes another tool in your tool bag / toolbox, whether you're a bag or a box person, I don't know. Bags are probably more stylish, right? No response, okay. It's okay. Just bag or box? Bag, okay, all right. Letter B, letter B. If we were approaching infinity, what would the answer be? If we were approaching infinity, what would the answer be? It would be 3, right? Because the top is actually a 3x to the first, the bottom is an effective 1x to the first, and it'd be 3 over 1. What would it be if we were actually approaching negative infinity? It would be negative 3, right? Because it would still be x to the first over an effective 1x to the first. We get the number first, and we get the SIGN sign second. And the top, when you plug in a negative number, it would give you a negative over the bottom, which is always positive. So this is kind of the same type of ratio that we've seen before when we analyze the end behavior. But we're not approaching the end of the graph, are we? We're approaching 5. From which side? From both. Let's try direct substitution. When I plug a 5 into the top, I get 0. When I plug it into the bottom, I get 0. Yay. Yay. Can we rat-con it? There's only one term, right? So we could rat it, but we're not going to rat-con it. Would ratting it work? If I multiply by radical over radical? I don't think I'd accomplish anything. Let's explore it. I'm not going to write all the symbols out, but we'll explore it because it is a viable method. It's not illegal. But in the top, we're left with 3x minus 15 times the radical of the bottom. And the bottom, radical times radical is radicand. Yeah, hooey. And now if I plug in, I'm still going to get 0 over 0 because it's still going to be caused by this now and that. So what that means then is maybe it's now turned into a factor problem. The top I could factor out of 3 and I get x minus 5 times the radical that's there. And that was the guy that was causing the 0. And in the bottom I could factor into x minus 5 times x minus 5. Well, there's what's causing the 0 down there. And yahoo, yes, the 0 over 0 problem goes away. Yeah. One of the 0 over 0 problem goes away. I'm still left with this, which remember caused the 0 when I plugged in originally. And I'm still left with another x minus 5 factor, which caused 0 over 0. So if I ended up with that, I could rat it again. And if I ratted it again, guess where it's going? I'm going in a circle. And I'm going to end right back where I started. Now, is going in circles better than going nowhere at all? I don't know. I don't know. It's like running around the track to try and get somewhere, right? You're just like, okay, I'm back where I started. You're going to burn some calories, but you're not really getting anywhere. So that's not what we want to do. Okay, so, hey, it was good to explore that. Any other ideas? Any other ideas? Yeah, absolutely. That method that we just explored kind of led us to the realization that the denominator under the radical actually factors, and it factors into x minus 5 times x minus 5, or x minus 5 squared, huh? Yeah? But now if I plug in, I still get 0 over 0. Schmuckers. What, you see something? You see something? The square root of something squared should just be the something. And what happens now? They divide out. And we're just left with what? 3. Was it that easy? Did that feel too easy? It kind of felt easy. You think that's what the answer is? Based upon the tone of my voice? Well, you can never really trust that. You know how I can really determine it? Here's how I can really determine it. Let's go ahead and graph it. Because the graph will tell us. If you're not sure and you have access to a calculator, it's okay to verify your results, especially in the privacy of your own home when you are practicing. You can verify it. Let's try it. I'm going to go numerator to denominator, and I got 3x minus 15. And then divided by the square root. You have to type in the original function, x squared minus 10x plus 25. All right, so there it is. I've got it typed in. It looks good. I'm going to hit zoom 6, which is a good place to start. That'll include the x equals 5 that we're approaching. Let's see if it approaches 3. What the? 5 is going to be right about here. The graph is not showing that the limit is 3, right? I typed it incorrectly. The graph is kind of indicating that the limit at 5 should be what? DNE, because the limit from the left appears to be what? -1, -2, -3. And the limit from the right appears to be +3. We just found the limit from the right, and we called it the general limit. What went wrong? We are incorrect. What went wrong? Yes. I got rid of the what? Yeah, it was the step where we simplified the square root. It should be plus or minus, absolutely. And then how would we know on which side was plus and which side was minus? It should be plus or minus. And I'll show you why. We've had this already. The square root of x squared and the square root of x quantity squared, if you're talking about just an expression, they both equal x. And that's kind of what we just did for the expression. But they're completely different functions. And you know why they're completely different functions? They have entirely different domains. The domain of the bottom one is x is greater than or equal to 0. Because the order of operations, you can't take the square root of a negative. But the top one has a domain of what? All real numbers, because you're squaring it first. In fact, the top one is another way to make any number positive. You square it to make it positive, and now you've increased its magnitude. So you take the square root of that positive number and get it back down to size. That's equivalent to doing what to it? Taking the absolute value. This is an identity that we've already seen this year. The square root of a quantity squared, in that order, when the square is under the radical, it is equivalent to the absolute value of x. If you were to graph 1 in y1 and 1 in y2, you would see no difference. So, over here, instead of just taking the square root of something squared and calling it x minus 5, we really should have called it what? The absolute value of x minus 5. And now we see something we recognize, right? This is Senor Salta. This is Jumpman. And because we know 5 is the value that's causing 0 over 0, and it's the general limit, now we know the general limit is what? It's DNE. And if we needed to find the limit from the left of 5, how would we do that? Good. Plug in any value less than 5, and if we need the value from the right of 5, plug in any value to the right. So that's another little clever strategy. Look for the square root of something squared to be called the absolute value. And that kind of takes care of, Hunter, the plus or minus, right? On either side. Okay. Questions on B? Kind of fun, kind of? More on the kind of or more on the fun side? More on the fun side. Okay, good. Letter C. Never not first. What do we get? Tangent of pi fourths. Ooh, what's that? 1. Okay, so the top is 1 minus 1, which is 0. And then sine and cosine at pi fourths are both what? Square root of 2 over 2. And if you subtract them from each other, you get 0. Hooray! It's got trig in it. Are we going to be using the trig limits, the two that we memorized? Why not, Zach? You're right, we're not. You said no. I thought that was no. You're right. Is right. No. To use the ones we memorized, Zach, we have to be approaching what number? 0. What are we approaching? Pi fourths. Now we know that we could be approaching pi fourths and still use those as long as we did what to our graphs? Shift them over. So if that were like tangent of x minus pi fourths and same thing here and same thing here, then we might be able to use it. But they're just x's, so they haven't been shifted at all, so that's not going to help us. So we need some other way to do it. You could do that. You could put 1 over all of that minus tangent over all of that. That's how that would work if you split it up. And I don't know if that would help or not. We would kind of still get, we would get 1 over 0 minus 0 over 0. That's what I would kind of lean towards. It worked on the other problems. If we could put everything in terms of sine and cosine, maybe, just maybe, that is a good first step. So let's try that. 1 minus tangent, which is, of course, sine over cosine, all over sine of x minus cosine x. And now, yay, hooray, hooray, we don't have to worry about what to do next, right? There's no guesswork in what to do next because we have created a complex fraction. And the next step is to eradicate it by multiplying by the LCM over the LCM of your miniature denominator, which of course is cosine. So if I multiply by cosine over cosine, notice I do have 2 terms in the numerator as well as 2 terms in the denominator. So I am going to have to distribute to both terms. What do we get in the numerator when I distribute the cosine? I get cosine x minus, and what happens with these cosines in the second term in the numerator? They divide out. So I'm just left with sine. Now on the bottom, do I want to distribute the cosine? Well, I'd have to distribute to both. Remember, you need to know what's causing the 0. It's the sine minus cosine pairing that's causing the 0. And if that weren't enough evidence, look what we just got in the top. We got cosine minus sine. So if I can leave a sine minus cosine factored in the bottom, I might be able to divide them out. But can I divide out a sine minus cosine and a cosine minus sine? I can factor out a -1. And since I haven't written the denominator yet, I'm going to go ahead and just factor it out of the denominator. So when I factor a -1 out of sine minus cosine, it changes both signs. So I'm just going to go ahead and write it like that. And then I'm left with the other cosine factor that was there from right here. And now the 0 over 0 problem is the cosine minus sine in the top and bottom. It divides out in the top, leaving a 1. And all we have to do is plug in now. And we get 1 over negative cosine of pi fourths, which could also be negative what of pi fourths if I bring it to the top? Secant. Are either one of those an acceptable free response answer? Yes, because they both what? Exist or not exist? Yeah, it's an actual point. Now, if you wanted to simplify it, because this would not be a multiple choice answer, what is cosine of pi fourths? Square root of 2 over 2. And of course, if I flip that, that's -2 over the square root of 2. which is also not going to be a multiple choice answer. If we rationalize that, we get negative 2 square root of 2 over 2, and that will not be a multiple choice answer because the 2's divide out. And so the prettiest answer is negative square root of 2. That would be the multiple choice answer on the no calculator portion. Free response to any of those answers from this line down would be acceptable. All right, so just because it has trig in it doesn't necessarily mean we're going to be using the trig limits that we memorized. That's why this one's in here. But putting things in terms of sine and cosine can help jumpstart a problem. All right, any questions on T? Letter D. We got the limit as h goes to 0 of sine of x plus h minus sine of x over h. So recall that the variable underneath the limit is the one we're treating as a variable, and any other variable that appears in our limit expression we're going to treat as a what? Constant. So we're going to treat this x as a constant, and the other one too. Treat them as a constant. So what happens if you plug in a 0 for h? I get sine of x minus sine of x in the top, which is 0, and of course 0 in the bottom. Yay! Now notice that the h in the bottom is causing the 0. What could I do on this one? Could I split up the terms? Could I put this over that minus that over that? Algebraically, I could. But would I be able to call sine of x over h as h goes to 0, 1? No, because they're different variables, right? If it was sine of h over h as h goes to 0, then I could. Yes. Very good. This right here is the problem. Sine of x plus h, I'm going to write it right here, was an identity that we had in pre-calc. Is it equal to sine of x plus sine of h? Try not to laugh as you answer. No way. No way. That's not that. Okay, this is a composite argument. So remember, sine is selfless, right? Me, you. Me, you. Okay. I'll go first. It's my identity, but cosine, now I'm giving you a chance. Right? Sine, same sign. So if it's plus, it keeps it. And then sine of the second, cosine of the first. That's the identity. While we're at it, let's review the cosine composite identity. If you recall, cosine is not selfless. Cosine is selfish. Me, me. Me, me. Me, 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 me. Then if there's anything left, then you. All right? So cosine goes cosine x, cosine h. Me, 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 me. Me, 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 me. And then, of course, what's the cost of being selfish? The sign changes. And then signs like relax. Cosine, there's plenty of terms for all of us. Relax. We're all getting on the airplane. It's assigned seating, cosine. Whatever. Okay. Do you have to know those? You do. You do. So that's why this falls under general cleverness. It's not clever if you know the identities, and it's not clever if you know when to use them. This is going to help us in this case. So I'm going to shrink those down if I can. Let's try that again. Because I need that space to work, so we'll put those over here. All right, so let's go ahead and use the identity now to do the problem. We still got to write the limit as h goes to 0. Build the shelf. We get sine of the first, cosine of the second, sine times sine, sine of the second, cosine of the first. And then, of course, we have the minus sine of x that's hanging out at the back. Now, notice what that did is at least got the angles to be the same. We now have the same angles, cosine of h and sine of h. Here's what we're going to do. Notice that this one, this in the middle has a sine of h over h, that middle term. That would be a good one, wouldn't it? Because if I could isolate that middle term over h, I could call sine of h over h what? As h went to 0. 1. So let's split that one up. So we'll get sine of h times cosine of x all over h. We'll do that. And then the other ones, we'll just leave them. You don't have to put every term over the denominator. You could put any combination of terms over the denominator. So I'm just going to leave those two together for now. Now, I like to evaluate the limit all at one time, so I'm not, otherwise it's kind of a notational burden. I'm just going to let these guys hang out for a little bit. I think he's ready to go, because I think my plan is to call that 1, and then, of course, if I'm treating x as a constant, then cosine of x is also a constant. And that should become cosine when the time comes. But what can I do in this second thing right here? Do I have anything in the top that is, I don't know, like common, like a common factor in each of the two terms? I do, right? I have a sine of x. So if I factor out the sine of x there, I'm left with cosine of h minus 1 all over h. Ooh, 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 ooh. You'll see something happen in there. The limit as h goes to 0 of cosine h minus 1 over h. Is that anything we memorized? That's equal to what? 0. I think we got it. We're ready to go. So in the first term, the highlighted part becomes 1 times cosine of x is a constant, plus sine of x is a constant, times the limit of cosine h minus 1 over h becomes 0. And because I plugged in at that step or evaluated, I don't need the limit. Remember, we're treating cosine x and sine x as constants. Now, anything times 1 is itself, and a constant times 0 is 0. So we just end up with cosine of x. And that's the answer. Now, what you're going to learn in section 2.1 is that this becomes the definition for the derivative function, what will be called the derivative function for sine of x. And you're actually going to memorize it. The derivative of sine of x is going to be cosine of x, and you're going to memorize that. Unless you just did, you don't have to memorize it then. What's the derivative of sine of x? Cosine of x. Now, you don't know what the derivative is necessarily, but you know that its derivative is cosine. And we just proved it right here. We just derived the derivative, which is kind of interesting. So right now we're just evaluating the limits, and trig identities could be helpful, even some of the more obscure ones. You're not going to have to use the half-angle identities or the power-reducing identities in here. All right, and the last one. Yeah, those were like the tangent of pi 30 seconds problem that was offered. All right, we have trig again. We're approaching pi thirds. What do we get when we use direct sub? Well, let's see. What's cosine of pi thirds? One half. What's 1/2 squared? 1/4. What's 1/4 times 12? 3. Oof, that was a lot of plugging in. I'm going to write that down. I don't want to forget it. Plus cosine of pi thirds is 1/2 again. What's 1/2 times 2? 1, and then we got the minus 4. So 3 plus 1 is 4, minus 4 is 0. Whew, that was a lot of work for 0 in the numerator. Can we just assume 0 in the denominator? No. Let's go ahead and plug it in. Cosine of pi thirds is 1/2. 1/2 of 4 is 2. 2 minus 2 is 0. Okay. It was, but at least not by assumption. Are we going to be able to use the trig limits that we memorized as x goes to 0? No, because again, we're going to pi thirds, and none of these are shifted over to pi thirds. Can we put everything in terms of sine and cosine? That got the party started last time. What's that? Yeah, it's already partying, right? It's already in terms of cosine. So that's not going to help. Yeah, can we? I think we can. Because I see a squared term in terms of cosine. I see a non-squared term in terms of cosine, and I see a constant. And I kind of remember somewhere in my math career, squared, non-squared constant was a trinomial that possibly was factorable, but we always did it with plain old x. Is it possible to do it with plain old cosine? I believe so. In fact, if you plugged into the denominator and got 0, that's like a 4x minus 2. Kind of like it, but instead of x, we have cosine of x. And the top would act like kind of like a 12x squared plus 2x minus 4. Kind of. But it's just in terms of cosine. So if this linear factor in terms of cosine in the denominator causes 0, maybe that is also a factor in the numerator that's causing 0. Is that probable or possible? Yeah. Let's try it. I'm going to go ahead and put 4 cosine of x minus 2 down here. And in anticipation that it's going to work, because I like to think positive, I'm going to put that factor in the top as well. Now, let's just see if we can come up with the other factor. If I need to multiply the first ones to get 12 cosine squared, and I already have a 4 cosine, the next factor in the front here needs to be a what to get a 12? A 3, and of course another cosine. And now let's look at the last term. I have a negative 2, and I need to get a negative 4, so this last term here needs to be a positive 2. And now all we have to do is check to see if we get the middle term. We need a positive 2 cosine. On the outside, I get a plus 8 cosine. On the inside, I get a minus 6 cosine. What's 8 minus 6? It's 2. It worked. Very good. This one does factor. Look for opportunities to factor quadratics that are not just functions of x. They could be functions of cosine of x. So once we realize that, those divide out. We got rid of the 0 over 0 problem. Guess what we get to do now? Direct sub. So cosine of pi thirds is again what? 1/2 times 3 is 3/2 plus 2. Free response, stop? Possibly. Multiple choice, keep going. Right. 2 is the same as how many halves? 4/2. So 4/2 plus 3/2 is 7/2. Yeah. Or 3.5. Either one is 3.5 terminates. So there you go. Look for factoring opportunities. Just another word about quadratics that are factorable. If this had been 12 cosine to the 4th of x plus 2 cosine squared of x minus 4, would that factor also? Yeah, as long as the exponent in front is twice as big as the middle exponent, it could possibly factor. This one would factor into 4 cosine squared of x minus 2 times 3 cosine squared of x plus 2. So that middle term, or the smaller exponent, is going to be the one that's a bit in each factor. What if it were the following? What if it were 12e to the 2x plus 2e to the x minus 4? Would that factor? That's a quadratic now, but not in terms of cosine. It's in terms of e. Because notice 2x is twice as big as 1x. That's going to factor into 4e to the x minus 2 times 3e to the x plus 2. So you could factor things that are not just plain old x. You could do it for logs as well. Let's do it. Yeah, so you can have log. Let's see, you want it ln? Okay. So 12 natural log to the 4th of x plus 2 natural log of x minus 4. That would factor into 4 ln squared of x minus 2, 3 ln squared of x plus 2. Or no, yeah, is that right? Yeah. Because you said ln to the 4th, these have to be, this would be squared, sorry, I didn't write that correctly. And of course, if we started just as 12 ln squared of x plus 2 ln of x minus 4, then it would factor into almost the same thing, but just linear factors of ln now. So yes, it works essentially with any function. So look for quadratic factoring opportunities. If you have 3 terms, variable is twice as big as the other variable's exponent, and you have a constant, it could factor. All right, we are DUNN. We are Brooks and Dunn on this Cowboy Friday.